Okay, so natural log base e, that special number we learned about, 2.718, blah, 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 blah. This is the log of that. ln. If you look on your calculator, there's an ln button. Yep. When you are taking the ln, the problem will say ln, natural log, and then that's the button you'll use. You're going to see we're going to use those in some word problems. But I want you to take special notice of this one. Because remember, ln is log of base e. So if I rewrite this, which you shouldn't really rewrite it, but just so that we can see what this looks like. It's e to the this equals this, right? So e to the what equals e to the 0.25. 0.25. So you can see that these are basically canceling each other out. They're like inverses of each other, right? If you have e to the something, if you take the natural log of it, you just get the something. That make sense? That's a really important concept with the word problems we're going to be doing. A similar idea here. E to the power you have to raise e to get 5. What are we going to get if we raise e to that power? Okay? So those are some important concepts there. All right. Graphing logs. This is where the transformations are going to be really helpful. So it says here we're going to use the inverse relationship of logs. Well, because think about this. If we graph this, which we've already graphed before, y equals 2 to the x, we know 0, 1, 1, 2, 2, 4, we should know this by now, 3, 8 are on here with an asymptote at 0, y equals 0. And now graph this on the same plane. Well, how do we graph a log? Well, when you graph a log, think about it as its exponential form. Log base 2 of x equals y. How could I write that using exponents instead? Just like we did back here, right? Log base 2 of 8 equals 3. I could write that as 2 to the 3. Oh, I don't know why it keeps doing that. 2 to the 3 equals 8, right? So if I'm graphing logs and I want to look at this, and I want to rewrite this as an exponential form instead of the log form, remember they are exactly equal to each other, what would be the exponential form of this? What to the what? Go ahead, I hear you mumbling it. 2 to the y equals x. Right? That's just what that log means. 2 to the y equals x. How is that related to this? Ding, ding, ding. It's the inverse. Remember when we were finding inverses, we just switched the x with the y? So this is the inverse. Okay. When you graph an inverse, what happens? What does that graph look like? I'll give you a hint. It reflects over a particular line. What does it reflect over? Nope. The diagonal line here. Remember that? It reflects over that diagonal line. What is the equation of that line? Y equals x. It reflects over the y equals x line. What does that mean for all of the ordered pairs? Yeah, they flip. So on the blue graph, 2 to the x, we had the points 0, 1, 1, 2, 2, 4, 3, 8, etc. On the red graph, we're going to have all of the inverses of that. We're going to flip them. 1, 0, 2, 1, 4, 2, 8, 3. That's what happens with an inverse, right? So 1, 0, 2, 1, 4, 2, 8, 3. See how they reflect over that line? So this is the graph of the log base 2 of x. That's that graph. All right, what is the domain of that graph? What are all the possible x's? 0 to infinity, right? So it has to be, there's an asymptote at x equals 0, so not including 0, and then to infinity. What is the range? Negative infinity to infinity. X-intercept? We got one right here. It's at the point 1, 0. So x-intercept at 1. Y-intercept? None. Increasing or decreasing over what intervals? Always increasing from negative, oops. Can only be on the given domain, right? So from 0 to infinity. End behavior. Limit as x approaches negative infinity of f of x equals actually we can't go to negative infinity. Sorry. The domain doesn't go to negative infinity, so we can't use that here. Limit as x approaches 0, right? Because x only goes to the left as far as 0. Do you understand that? Our domain is from 0 to infinity. So when I'm saying the end behavior on the left, right? End behavior on the left, well, the leftmost point of this is 0. We can't go past that. So you can't say the limit as x approaches negative infinity because it doesn't go to negative infinity. It only goes as far left as 0. So we have to say the limit as x approaches 0, but that is still the left. That is still the left behavior. What is it doing as it's approaching 0? What is the function approaching? Where's this going? Negative infinity. So the right behavior, limit as x approaches infinity, where's that going? Also to infinity. Asymptotes, there's going to be an asymptote only at the vertical at x equals 0. Okay, so the question came up, how did we know that the asymptote was at x equals 0 here? So remember, with an inverse, the domain of the original function is the range of the other one, and vice versa, right? So on our original, this blue graph here, our asymptote was at the x-axis. So when we flip it, it has to be an asymptote at the y-axis. Does that make sense? You know, because it's the inverse. So this asymptote that was horizontal now became our vertical asymptote. Okay, so let's look at graphing some of these. Okay, so first it says identify the parent function and then explain the sequence. Okay, identify the parent function. What would be the parent function here? The parent function is just y equals log of x, meaning base 10, right? Because there's no base there, it's an invisible 10. All right, what's going to happen to that? Well, they have an x minus 1, a subtracting 1 from the x, because there's parentheses around that. So it's literally x minus 1. How is that going to move your graph? To the right 1, exactly. What does the 3 do? There's so many different words for this, but it expands it, it stretches it. I don't know, there's lots of ways people... So I'm just going to call it a stretch of 3. All right, you guys try the one on the right, number 2. Questions on those transformations? Okay, so then we have to put this into actual action here. F of x equals 2 log base 3 of x minus 4. In order to graph this, first we have to think about the parent function. What is the parent function? Log base 3 of x is the parent function. Log base 3 of x. The base is important. That's not that has to be part of the parent function. So, to graph this, rewrite it in exponential form. This is what to the what? Equals what? 3 to the y equals x. So, okay, so log base 3 of x is equal to 3 to the y equals x. We said we're going to graph the inverse of that because it's easier to graph y equals 3 to the x. So when x is 1, y is 3. When x is 0, y is 1. When x is 2, y is 9. When x is negative 1, let's just do a negative, we've got 1/3. So we should get a general feel for what this looks like. 0, 1, 1, 3, 2, 9, negative 1, 1/3. You're going to see that all of these exponential graphs are really similar to each other, right? This looks a lot like 2 to the x that we kept graphing before. Now it's just 3 to the x, so it's a little bit different, but that's what the graph looks like. So the green graph now is the inverse. What we're really trying to graph is the parent function, which is log base 3 of x. So all we have to do is flip these values, right? So log base 3 of x is going to flip these. 3, 1, 1, 0, 9, 2, 1/3, -1. So 3, 1, 1, 0, 9, 2, 1/3, -1. And this is our log base 3 of x. The blue graph here is the final graph. Now the first one always, takes the most work. This number 2 has the same parent function. We don't have to redo that. We already have the same. This is our parent function. This green one is our parent function. Well, is the inverse of our parent function, right? All the way along. So the parent function is the red one. Oops, now I'm in green. This parent function goes for all of these on this page. So you can start with that one on all of these. That's the parent function for the whole page. So you don't have to graph, so many times anymore. Number 2, you have reflection over which axis? Reflects over x. What does the plus 5 do? Up 5. So our original parent function is in this red box here. If we're going to reflect over the x-axis, what's going to happen to all these points? Reflecting over the x-axis, what's going to happen? Do the x values change? No. What happens to the y values? They become negative, right? So reflecting over x, should probably make this a different color, gets me 3, -1. 1, 0, 9, -2, 1/3, 1, right? So 3, -1, 1, 0, 9, -2, 1/3, 1. This is the reflection over the x-axis. Now we got to move the whole thing up 5. So you take all of these points and go up 5. 1, 2, 3, 4, 5, put a point. 1, 2, 3, 4, 5, put a point. 1, 2, 3, 4, 5, put a point. Still an asymptote at the y-axis, x = 0. Okay, so remember, this red box here on this page is the parent function for all of them. So your transformation just happens to those points. Now, you can write a new XY chart that reflects the transformations. You actually kind of need to make it bigger because there's not a lot of room here. Sometimes you need more columns. Oopsie, that's interesting. So what we want to do is cut the whole thing in half. So that's going to half the y's. So we got x is 3, right? Y is going to become 1/2. But then we're going to change the x again by moving it to the left 2. So where the x is 3, well, I'll put the original, 3, 1, right? The new x, since we're moving it to the left 2, we have to subtract 2 because we're moving it left 2. So what's the new x going to be? 3 minus 2. Well, what's the new y? Well, the new y, if we take 1/2 of it first, and then this is going down 3, right? So we have to subtract 3 again. So the old y was 1. Take half of it, what do you get? Now subtract 3. 1/2 minus 3. Right? And if you do that with all of these points, 1, 0 is our original. Subtract 2, you get -1 for the x, right? Take a half of the y, half of 0 is just 0, and then subtract 3, you end up with -3. So your final point here, you got to keep track of what your final ones are, right, is 1, -2.5, and then -1, -3. Nine, 2, subtract 2 from the x and you get 7. Take a half of the y and you get 1. Subtract 3 from that y and you get -2. So 7, -2 will be on your original. So again, this is kind of another method. If you would rather graph the parent function every time and then count, you know, take half and count, you can do that. This is just giving people another method if they want to do it this way. So 1, -2.5, -1, -3, 7, -2, and this moved to the left 2. So where our asymptote used to be at x equals 0, now our asymptote is going to be at x equals -2. Right? Because the parent function has the asymptote at x equals 0. So if you're moving it to the left 2, that's going to move your asymptote to the left 2. What's this number 4 going to do? Just in words, what's it going to do? If you have a -x, what does that mean? Yes, reflecting over the y-axis. which remember changes all of your x's, the sign of all the x's, right? And then what's the plus 1 do? Up 1, because it's not in parentheses with the x, so it's just going up 1. Okay, I'm going to have you try to graph that one.